Today we are going to discover how we solve a customer issue to detect substance violation in their factory, and we achieve this using the ONNX models and a tool from SAS called SAS Event Stream Processing. What we would like to achieve for this customer is they're using their existing camera, in this particular scenario we're 12, to detect if one of their employee was entering some dangerous area where machinery was moving, and in such scenario provide an alert. The key focus area for this engagement was the ability to detect people using an open source model from ONNX Model Zoo, and deploy this in production using multiple cameras. We stated it was 12, but could be more in the future. We are discussing for expand this to additional factory, where will be up to 40 cameras for each factory. And this need also to be integrated along with the downstream system of the customer to process and send the alert violation, but also to monitor the health of the system, ensure it's up and running, and eventually notify the customer about issues, for example, broken camera, that's allow them to repair promptly. This solution was achieved thanks to one of the SAS tools called SAS Event Stream Processing. SAS Event Stream Processing is part of the complex event processor family, so is a tool able to analyze in real time millions of events per second, and achieve so by using a publish-subscribe interface. The data in streaming come to the publish interface are elaborated by the tool, apply some algorithm. In this scenario, we apply computer vision algorithm, but also geofence algorithm to ensure that the people were or not in the wrong position. And then, once we have a result, we publish this result to another source. This tool is also engineered for agility, so has a very small footprint that allows him to run in the smallest device, like Raspberry or NVIDIA Jetson, but also scale to biggest system like cloud or big edge solution, like in this scenario. This tool could be accessed, it could be developed using online graphical studio, SAS ESP Studio, that allow you to draw the flow of the data, and apply all the transformation needed to fulfill the requirement of the algorithm you need to run. It's also possible to create a run model in a standard Jupyter notebook that is usually used by data scientists. Once you develop the model and you are ready, then you could use another tool called SAS Event Stream Manager to place this in production and monitor the status of this project. What we did together with Microsoft is integrate the ONNX runtime inside of Event Stream Processing, allowing the customer to access the capability using the standard interface and the other facility from SAS Event Stream Processing. To integrate this, we allow to achieve from our customer to get the ONNX model on their favorite frameworks. That could be also SAS. We also have a framework called Visual Data Mining and Machine Learning that is supported in ONNX, but also from Kafka, PyTorch, common machine learning frameworks. This ONNX model then is processed, is attached to an ESP Studio model that allows them to transform, for example, to modify the picture that is coming to the flow in a format suitable for the model. And then the model, along with the project, is shifted to the ESP server that, thanks to a plugin we developed, could use the facility to the ONNX runtime, and then also leverage the execution provider for the hardware acceleration. The beauty of our solution is that we ship all together in a Docker container, including the driver from CUDA or TensorRT, including OpenVINO to run on CPU. What proposal we suggest to our customers? Since they have this requirement of ensure that they detect violation and to be resilient, we suggest them to a modular solution that split the activity needed for process this image in several steps. And each step then is using Kafka as a buffer queue to ensure that if something goes wrong in one of the processing, the full flow, the full pipeline is not harmed. We could just keep the data in the Kafka, and then when one of the processes is restored, we are able to continue the flow. The first step, of course, is acquiring image from cameras. I will see that we have one step for each camera to ensure that if there is one problem, not all cameras are affected. Then we have a model that processes the computer vision and level a GPU that user has scarce. So we condense in this model all the requirement for computer vision processing, and then we have another model that is responsible for post-processing. To see this in the real deployment, we have this image. So, important to note, we deployed this with what we call workload in the edge in a Kubernetes cluster. So it's a more bigger edge that we used to, but still an edge solution. Let's use Kubernetes as a deployment mechanism. And then we also have, of course, we connected with a centralized cloud solution to monitor this cluster, and in the future to monitor more cluster that will be more factory from a central location. In the workload inside the edge, as you see, the step one is the ingest the video. And we have one pod inside the Kubernetes for each camera to ensure that nothing could happen. The camera cannot harm the other camera. There's no possibility that we lost more than the camera that at the moment are not really working. All this ingest video is placed on a Kafka bus and then processed by another pod that's running ESP, that's processing and read the image from Kafka and create the result of the publish the result of computer vision model. This pod, the number 3, is complemented. This is optional, but it's usually important by some additional sensor data from the customer that allow us to understand if the equipment that we are recording in the video of that particular camera are active or not. This, of course, is important because it's usual that people will go to the field to repair machine where I stopped. It is allowed, it is not an alert. But of course, this is completely different if the machine is running. In this case, we need to enforce the rule and send an alert in case the people enter in the space. So we say that the pod, the process 3, she will send back the data to Kafka bus, of course. Possible to check along with a database of location in each camera. Each camera could have multiple locations that are dangerous, and of course we have multiple cameras, so we have a database that registers all the dangerous location, and we read this database and we determine if the coordinate of the person we detected on the step 3 are inside or outside this area. If inside, we write out an alert that is then processed by the step 5 that is responsible to save the image to a solution, could be SharePoint or another report in CV. And then we have the step 6 that send to the system the alert along with the path of the image with the violation. This process is complemented with some heartbeat solution to check all pods are running, and also a process fault solution that ensures that if something wrong, for example, if a camera doesn't work, we automatically inform the app system. Worth to mention that this architecture is currently in production at one of our customer facilities, and we are currently working to expand this to more than 20 plants in the coming months. This slide highlights the key benefit of this solution from our customer perspective. The ONNX Runtime Integration ensures an optimal time to value, thanks to public available pre-trained models and the reuse of customer assets. This permitted us to reduce the overall project timing to less than a month. The architectural resiliency was another key benefit, and this was ensured thanks to Kubernetes and Kafka. Performance and scalability, especially, are other fundamental aspects of this architecture. Having centralized the usage of GPU to a single pipeline modules ensure an efficiency in hardware acceleration and also enable scalability by allowing to increase the number of GPU when needed. Finally, the solution allows to increase the number of cameras easily and provide support for different kinds of post-processing analysis beyond the fence used in this scenario. As an example, we could introduce a logic that counts the number of people in an area to avoid crowds, or we could verify that a machinery is not performing dangerous actions. This is all I have for today. Thanks a lot for listening, and feel free to reach us for any question at the address shown in this slide.